Hello everyone, I am Parthasaarathy from Tampere University. Welcome to my presentation on assessment of self-attention on learned features for sound event localization and detection. First of all, I would like to thank Archontis, Politis and Konstantinos Drossos, the co-authors of this work. So, coming to the motivation of our study, the most common way to solve cell tasks using deep learning techniques is to employ a convolutional recurrent neural networks known as CRNNs. The CNN layers are used to extract high-level features from the input audio, which is usually recorded from multiple microphones, and then the RNN layers learn temporal relationships on top of that. Over the years, RNNs have been very successful in learning these temporal features, especially in the field of natural language processing. However, the major drawbacks of RNN are their slow training and inference time due to the sequential processing and limited capabilities to capture very long temporal dependencies. Recently, we are seeing a significant number of research works in NLP as well as computer vision that tries to address these problems using self-attention mechanism. So we were interested to study the effect of self-attention mechanism in a cell setting. We wanted to exclusively capture the effects of self-attention, so we did not alter the baseline convolutional feature extractor given in task 3 of this year's DCASE cell challenge. We did not want a situation where we couldn't conclude if the improvement or reduction is due to self-attention mechanism or it's coming from somewhere else. So here is the baseline model used in this year's challenge. It's a typical CRNN network with 3 convolutional blocks and 2 GRU RNN layers. A typical method to predict the output is usually having 2 branches of fully connected layers. One branch detects the presence or absence of sound classes, which is a classification problem. The other branch predicts the location of the sound sources, a regression problem. Then usually a masked MSE loss function is employed, which considers only the location predictions when the sound sources are detected. But for this year's baseline, a simplified loss function proposed last year by one of the winning teams in DCASE 2020 is used. It is the ACC-DOA loss function, which is short for activity coupled Cartesian direction of arrival. So it simplifies the process. We no more require 2 separate branches for detection and localization. We just have a single branch for localization. The detection probability is calculated as the magnitude of this predicted localization vector. Then this magnitude is thresholded to determine whether a sound class is active or not. So this will be our baseline for this study. As I mentioned earlier, we wanted to exclusively study the effect of self-attention. So we replaced only the RNN layers in the baseline with self-attention block, and everything else remains the same. We carried out several experiments to empirically determine the best hyperparameters for our self-attention block. We have 4 main hyperparameters to tune in case of self-attention block. One is simply how many layers of self-attention we should use. Remember that we had 2 layers of RNN in our baseline. Next, we need to tune the number of attention heads in each layer. Each attention head helps a particular time step to attend to another time step. So by increasing the number of attention heads, we can make each time step attend to more than one useful time step. Then we have to choose the attention size. For most of our experiments, we stuck to 128 since the RNN in the baseline also had a hidden size of 128, but we also played around with 64 and 256. Next, we can have a position embedding. In RNNs, we know that the data comes in sequentially. The biggest advantage of attention layers is that we feed all the time steps at once. So adding a position embedding may help the model to understand the sequence characteristics. Finally, we had to decide how to connect successive self-attention layers, whether they could be connected directly or we need a residual connection with layer normalization like the attention is all you need work does. For evaluation, we trained our network on the DCASE 2021 Cell Challenge Task 3 dataset on the development dataset. It contains 600 1-minute recordings of 12 different classes. We trained all the model for 100 epochs and chose the model with the best validation score. We used Adam Optimizer and employed ACCDOA, which means we can train the model just with MSE loss. As far as metrics are concerned, we have detection error rate and F-score for the detection metrics. Note that the detection is considered true positive only if the predicted location deviates less than 20 degrees from the ground truth. For localization, we use the localization error and recall metrics. Here again, these scores are class dependent. The audio class has to be predicted correctly. So these are our results for various hyperparameter settings. So here n denotes the number of attention layers, m the attention heads, p denotes whether we use a position embedding or not, and ln denotes whether we use a layer normalization and residual connection to connect successive attention blocks. So we ran all the experiments 10 times and report here the mean scores and the standard deviation. The best performing model, as you can see here, has two self-attention blocks with 8 attention heads, positional embedding, residual connection, and layer normalization between successive blocks. So from the results, you can see that there is a significant improvement in the F-score and the localization recall metrics compared to the baseline, and a decent improvement in the detection and localization error rates. So this represents our best model, 3 convolutional blocks as in the baseline, followed by 2 self-attention blocks with 8 heads and residual connections and layer norm between the blocks. Position embedding is added to the input of the first block. So to summarize, we studied the effect of self-attention layers in cell task. Our experiments clearly show significant improvement in the F-score and localization recall metrics compared to the baseline CRNN. Using a self-attention also boosts inference speed, although the model has twice the number of parameters compared to the baseline. It's almost 2.5x faster than the baseline model. So this will enable us to use these kind of self-attention based models in time critical applications. That is all for now. Thank you for all your time and patience. Feel free to contact me, and the link to the paper can be scanned using this QR code. Thank you.